operating of converging and diverging nozzles. By combining the isentropic flow and normal shock relation, plus the concept of sonic throat choking, we can outline the characteristics of converging and diverging nozzles, isentropic flow, and normal shock. Plus the concept of sonic truth. At first, consider this picture for converging nozzles. This picture shows the converging nozzle sketch as shown in this picture. This is a converging nozzle. There is an upstream reservoir at stagnation P0. The flow is induced by lowering the downstream outside or back pressure PB. This is back pressure. Back pressure is in this smaller than the stagnation pressure, resulting in the sequence of state A to E shown in the picture. And C have also the various flow as a function of the ratio of the sonic pressure on the stagnation pressure. For a moderate drop in PB to state A and B, the throat pressure is higher than the critical value P0. The throat pressure is PC. The flow in the nozzle is subsonic throughout and jet exit pressure PC equals to the back pressure. For the moderate drop in PB, let me write for moderate. We have moderate drop shown in the case A and B. We have these diagrams. The throat pressure is higher than the critical value. P star that would make the throat sonic. The flowing nozzle in subsonic throughout and the jet exit pressure PC equals to the back pressure. So the flow in the nozzle in this case as subsonic in the nozzle and PC equals to the back pressure. The mass flow is predicted the subsonic isentropic theory and is less than the critical value m dot max. Let me write the mass flow is m dot for case A and B. Here m dot is lower than the critical mass flow. For condition C, let me write in the next page and consider the picture here. Condition C, this diagram. The back pressure exactly equal to the critical pressure. P star equals to the truth becomes sonic the jet exit flow is, and we have PC jet exit flow back pressure and the mass flow equals to the maximum mass flow as shown also in this picture. We have this diagram as truth and the back m dot equals to the maximum of the volume flow. The flow upstream of the throat is subsonic everywhere. We have also subsonic in the nozzle and predict isentropic theory based on the local area ratio. Finally, if the back pressure is lowered for the two conditions D or E, the pressure for D or E, we have these two conditions. The pressure P D and P star less than the stagnation pressure, the nozzle cannot respond further because it is choked at the maximum throat mass. Choked at the maximum throat mass flow. The throat remains sonic with P at point C equals to the back pressure, to the sonic pressure, and the nozzle pressure distribution is the same as the previous state C, as shown in this picture. The exit jet expands supersonically so that the jet pressure can be reduced from P star down to the PB. The jet structure is complex and multi-dimensional and is not shown here. Being supersonic, the jet cannot send any signal upstream to influence the choked flow condition in the nozzle. Choked, no signal at downstream. If the stagnation plenum chamber is larger or supplemented by a compressor, and if the discharge chamber is larger or supplemented by a vacuum pump, the converging nozzle flow will be steady or nearly so. Otherwise, the nozzle will be blowing down, with P0 decreasing and PB increasing, and the flow state will be changing from, say, state E backward to the state A. Blowdown calculations are usually made by a quasi-steady analyzer based on isentropy steady flow theory for the instantaneous pressure P0 and PB. The next operating in nozzle is the diverging and converging nozzle. Now consider the converging and diverging nozzle sketched here. We have a truth diverging area and converging area here, and also maybe have a possible shock, normal shock here. If the back pressure PB is low enough, if the back pressure is low enough, there will be supersonic flow in the diverging portion and a variety of shock wave conditions may occur. There will be supersonic flow in the diverging portion and a variety of shock waves. Condition may occur for curve A and B in this picture, these two curves. The back pressure is not low enough to induce sonic flow in the tube. Is not low enough to induce sonic flow in the tube. And the flow in the nozzle is subsonic throughout. The pressure distribution is computed from subsonic isentropic area change relation. Subsonic isentropic area change relation, such as the previous description for curve C and curve C here. We have also some the area ratio exactly equals to the critical ratio. MC on S star for a subsonic Mach number. The truth becomes sonic. And the mass flow reaches a maximum as shown here. M dot equals to M dot maximum. Now jump for a moment to curve H. Here PV is such that exactly correspond to the critical area ratio PV, or we can the ratio of PV on P stagnation correspond to the critical area ratio for a supersonic Mach. The diverging flow is entirely supersonic. including the jet flow, and PC equals to BB. This is called the design pressure ratio of the nozzle. And is the back pressure suitable for operating a supersonic wire tunnel or an efficient rocket exhaust? Is the back pressure suitable for operating a supersonic wire tunnel or an efficient rocket exhaust? Examples are available in the chapter also. Now back up to the suppose that PB lies between curve C and H. So, which is impossible according to purely asymptotic flow calculation. The pad pressure D to F accurate. The truth remains choked at the sonic value, and we can match PC equals to PB for the case D to F. The truth remains choked. At the sonic value, and we can match PC equals to PB by placing a normal shock at just the right place in the diverging section to cause a subsonic diffuser. We have subsonic diffuser. Flow back to the back pressure condition. The mass flow remains at maximum. At back pressure F, the required normal shock stand in the dark exit. At back pressure G, no single normal shock can be do the job, and so the flow compress outside the exit in the complex series of the oblique shocks until it match PB. Back pressure F. The required normal shock stand in the duct exit. Duct exit. At back pressure G, no single normal shock can do. For G, no shock can do. Finally, a back pressure I, PB is lower than the design pressure H. Let me write for back pressure I. PB is lower than design pressure H. But the nozzle is choked and cannot respond. The exit flow expands in a complex series of supersonic wave motion until it matches the low back pressure. For further details of design jet flow configurations, note that for PB less than the back pressure C, there is supersonic flow in the nozzle. And the throat can receive no signal from the exit valve. The flow in the nozzle and the throat can receive no signal from the exit valve. The flow remains choked and the throat has no idea what the exit condition. What the exit condition are. The flow remains choked and the throat has no idea what the exit conditions are. We said here before. Note also the normal shock patching idea is idealized. Downstream of the shock, the nozzle flow has an adverse pressure gradient, usually leading to wall boundary layer separation. Blockage by the greatly thickness separator layer interacts strongly with the core flow and usually induces a series of weak two-dimensional compression shocks rather than a single one-dimensional normal shock. The next section is about the compressible dark flow with friction, which are not mandatory in this course. You can read by yourself from the reference, but we have a section about Prandtl-Meyer expansion waves in the next video.